And hello everyone, welcome to our discussion of turbulence modeling. Today we want to start something a little bit different from where we were. So we want to talk about turbulent heat transfer. So in the last, I think most of the series actually talks about fluid mechanics and how turbulence is modeled as increase in viscosity or momentum diffusivity for the momentum equations. So for heat transfer, something similar is being done when you change or filter or average these energy equations, and you give it something. You also increase the conductivity or thermal diffusivity artificially. So you model the increase in turbulence as some increase in thermal diffusivity. So before I go into more detail, let's just like to tell you about where I get my references from. First is from Bejan, Convection Heat Transfer, the 2013 version. Also, for some of the basic implementation of the energy equations, which we are going to talk about shortly, you can take a look at the links over here. I'll paste it in the description as usual. These are in the OpenFOAM energy equations. Okay, so here you can find these, and you can find roughly how these equations are being put into a real CFD code like OpenFOAM. And if you want to take a look at the source code, you can go here, and from there you can go and just explore what the code is like. Again, that is in the description. So usually we can do this. Okay, you go into this file where you can go where you will find turbulence models are in the applications folder, and you go into solvers. Then over here you will find the heat transfer, I believe. Heat transfer. Okay, then you'll find some of the solvers here. You go into buoyantPimpleFoam, for example, then you will be able to find your E equation and U equation. So E equation is for the heat transfer bit, of course. These are energy equations, and you can see that HE here, this would usually represent something of an enthalpy formulation. So let's begin. Okay, we will have our usual first law of thermodynamics come into play. This is just conservation of energy, nothing more, nothing too complicated. Yep, so we'll start with those basics. Yeah, so this is the first law. Okay, this is just the energy conservation. And what do we have here? We usually have, we start off with the defining internal energy. So we do it in terms of internal energy, but you know the internal energy symbol is usually U, but because we have in fluid dynamics U also representing velocity, so we don't want to confuse ourselves. So what usually is done is to replace the notation of U with E. So E is the internal energy. So for example, if we have our enthalpy equation, I assume you're already familiar, H equals to U plus PV. That's what's usually written in thermodynamics textbooks. But here we will write H equals to E plus PV. So this is how we try and differentiate E, or I mean internal energy, from the velocity or the velocity vector. I mean, we can sometimes use V as well, but we generally try to make it easier for us to differentiate between the energy quantity rather than the velocity quantity. Because if you put velocity as V and then internal energy as U, you could easily mistake some of it for momentum equations, even though the terms are different. It will cause some confusion for you. So that's why we try and put it in terms of E rather than U. So what do we have here? Here we have the time derivative terms. Alright, so you have the substantial derivative, okay? Substantial derivative of E Okay, this part actually deals with the compressibility part. Okay, I mean after you do your little derivation in your own control volume, and you do your product rule, this term will pop out, and actually the quantity in the parentheses on the left side of this equation, this term I'm talking about, this will be equals to 0, because if you recall what the continuity equation is like, you'll see that, or rather not continuity equation, we haven't talked about incompressible assumption yet. We'll just say because of mass conservation, this whole thing will just drop to 0, which makes this a lot easier. Okay, so I'll go through term by term. So this is the divergence of the heat flux. This is usually due to conduction or some other terms as well. You could even put in a radiation kind of a heat flux in here if that is significant. Okay, so this is where all the external heat flux will come in from. Okay, now we also have I mean, of course you can separate this term out into the conduction and radiation heat flux. That's not a problem, but yeah, radiation is another level of complexity, so for now we'll just stick to conduction first. Then if we want to put in radiation, then we'll consider that later. We also have this this term here. It's a heat generation term. It's a heat generation term, and you can also put a sink term as well. You can have a endothermic reaction, for example, and this term here will be negative. If your reaction is exothermic, then of course this term will be positive. Okay, so for example, you have a fire that's burning, and then you want to use this equation to model a fire, then this term will definitely be positive. This term here, it's somewhat of a flow work equation. It's not quite flow work. Yeah, it's not quite flow work, but it's somewhat related a little bit to flow work. All right, meaning to say that there's some PV work in and out. So this actually corresponds to the sum of the pressure times the specific volume, and then you have it going in and out of the system. But this is conceptually related but not exactly the same, so you can think of it in that regard. Some PDV term, so to speak. Yeah, PDV term. Right, because the first law, you also have to consider work done on the system or work done by the system. So this one will constitute the work done term. All right. So depending on your simulation, this may or may not be significant. Right. So this is the last bit, which is called the dissipation term. Okay. So dissipation term is basically when you have frictional forces in the fluid, and then some of that energy gets dissipated into heat. So for example, from your turbulent kinetic energy equation, your dissipation term, will subtract from the turbulent kinetic energy, and it has to go somewhere. That somewhere is over here. Okay, it's over here. And you don't just, you can have energy not just from the turbulent kinetic energy. You can have, just normal friction acting on laminar flows, and that will also constitute some of that kinetic energy being transformed into this internal energy or heat. And normally we like to work in terms of enthalpy, because as we all know, okay, dH dt, you change dH dt, this definition of Cp is as such, right? So from Thermodynamics 101, so should be very familiar with this, I hope. Yeah, we like to always use this constant pressure heat capacity, and that's always related to the enthalpy of the fluid or the solid, whatever have you. All right, so And most OpenFOAM solvers or CFD solvers, they like to work in terms of enthalpy anyhow. So that's what we will try to use. So for enthalpy, we know that H equals U plus PV, or in this case, we want to use H equals E plus PV. Where if this is the specific enthalpy, this is the specific internal energy, then we'll have pressure times the specific volume over here. Specific volume is of course 1 over rho, okay, where rho is the density of the system or the little fluid package. So you will have H equals to E plus P over rho. Now if you want to go and take a look at the left hand side, okay, I'm just going to rewrite to make it simple. This whole term here disappears. Remember, this thing is 0. This thing is actually 0. And this whole term here, this whole term on the left disappears. Okay, this is mass conservation. Okay, so this whole thing, yeah, this whole thing equals 0, and we want to change this into an enthalpy form. So we'll try to have a form of the left hand side first. So what we'll have is dH dt. Okay, this should be a capital D. This is a substantial derivative. Then we'll just apply product rule, quotient rule, what have you, etc., to do this little differentiation here. So first thing first, dE dt is pretty obvious, and I'll just do a plus. I'll do this, yeah, and this term here, we'll just use the quotient rule here. Very simply to put, we have the bottom constant. We'll differentiate the top. Okay, and we subtract the top, and then we differentiate the bottom, and we divide by the bottom squared. And this should be, oops, I don't want to delete all that work. This should be equals to, right, 1 over rho here, 1 over rho here, and this will be just then divided by rho squared. And I'll cut and paste and put this at the bottom. There you go. This is the equation you will find yourself in. Then you kind of try and substitute this dE dt, because you can just get rid of dE dt and say this is actually the dH dt minus whatever we have here. Alright, and we substitute that into here. Substitute. Okay, and we'll put this like so. Alright, now first thing first, there's a density term here, so I'll just multiply that in. This thing I'll just cancel. This thing I will say is just by rho. Okay, and I'll bring this other term to the right hand side, and that's sort of almost there. We're almost there with the enthalpy equation. Yep, and what then we have is we'll have this term here, is a pressure term, and then we'll have this other term over here as well. Okay, we'll have this other term here as well. So I'll just bring this term out. This is a pressure term out. Cut and paste here. And for the sake of convenience, I like to combine these PV terms together. This work done here. These are PV terms. Yep. So what I do is I just divide my rho and times rho, and I can factorize this term in. Alright, so I'll put a negative sign outside here, minus sign here. I'll bring this in. I'll get rid of this. and I can factorize out P over rho, and then we'll find something pretty familiar. We'll have this d rho dt, the substantial derivative, and of course this rho times the divergence of velocity. That term is actually this term here, which very nicely we can just cancel and put as 0. Alright, so what we have at the end of the day, we have this rho dH dt, and then we have the heat flux term, we have this heat generation term. Okay, this is the dissipation term again. This dP dt term, and this dP dt term, I guess you can think of it like this. If you remember your thermodynamic relations, or I can put it like this: dE equals to T ds minus P dV. Okay, and then dH equals T ds plus V dP. Okay, this TdS term, I guess you can sort of think of it as all the stuff over here. This term would then correspond to this VdP term. Okay, of course this is for closed system, so there will be no inflow outflow, which actually these convection terms in the substantial derivative deal with. But these terms deal with the heat flux terms over here, and of course to some extent the source term. Okay, this is just a heat added to the system. Then you have this dP dt term, which is you can think of it as this VdP term. Alright, this term for incompressible fluid, if you change around this equation a little bit, this term will usually disappear. So let me show you why. Okay, so this is just still fundamentals. Okay, dH equals to Cp dt plus 1 over rho 1 minus beta t. And this is the expansivity coefficient. That's after you do all those thermodynamic calculus mumbo jumbo. Yeah. So what this does, this is from thermodynamics. We can of course change this into a substantial derivative. Okay, we can change this into a substantial derivative, and of course we multiply rho throughout. So we have rho rho throughout multiplied, and this from thermodynamic calculus. I'm not gonna do those here. Yep, we will get this equation. Yeah, so you have all the funny relations. Okay, those relations are important to know. Just write them out or not derive them. Rho partial T P. This is definition, I think, and of course partial S partial T P equals Cp over T. So that's how we try and get all of these equations out. So we have these equations out here. Now we want to replace dH with dH dt, the big D's. Alright, so we do that. Alright, so dH dt dt. Alright, and then we'll do the same here. dP dt. Okay, so we can actually change this term on the left to this term on the right using some thermodynamic calculus. Why is that important? Because we can substitute Yeah, my mouse just disconnected a little bit there. But anyway, we can substitute this term in here so that we can make this term, this actually dependent on temperature. And what do we notice? This term actually cancels with one of these terms here, so that we can just write the following beta t, okay, on the right hand side. And usually if incompressible, the beta equals to 0, because the fluid is technically not compressible, so this term over here disappears, making our life very easy and simple. Okay. Yeah. So for ideal gas, okay, beta is not 0, beta equals to 1 by T, then you will have a slightly different form of this equation. Yeah, you have a slightly different form of this equation, and this will be like the following, just like this. Okay, so this is how your basic energy equation comes about. These are the terms in here, and of course we can use Fourier's law to substitute inside this heat flux vector. And what we do is just the following: we get rid of the negative sign, you put K and the heat flux gradient in, and this is our usual final heat equation. Okay, we have generation term here. We have the dissipation term here, which is usually negligible, except for okay, for example, lubrication and flow of viscous fluids. All right. Okay, hold on. I think I made a mistake here. I want to put this here. Right, this is the correct version. All right, that's if you want to put it in terms of temperature. Yeah, it's in terms of temperature rather than, let's say, H. But usually, of course, for code here, they like to put it in terms of H. So in whichever way suits you, that's fine. Yeah, but probably, the way they do it in OpenFOAM, there's a big so-called reliance on the doing it in terms of H instead of, let's say, temperature. Okay, that's just technicalities. This is what the dissipation terms looks like. Okay, it's a lot of strain rates. All right, and this one is the summation of the square of this strain rate, specifically del ui del xi. So it goes from I equals 1 to 3. This one is slightly different. This one, it's you sum it first and then you square it. Okay, so that's all we have. In the next video, we try to do a little bit of these averaging again. Okay, because it's very important to know how these terms are averaged so that we can do our closure relations and modeling later on. Thanks for watching. I'll see you guys again. Bye bye.